Welcome you all again for the thermodynamic lecture series. So in this today's lecture we are going to solve a problem on isentropic process which is based on steam table and also Muller chart method. So before getting into the problem, so we need to know what is the state of the steam. Okay, so there is the condition of the steam or the quality of the steam we need to identify. So for that we all know that they are having three different conditions or quality of the steam is available. The first one is wet steam, and second one is dry steam, and third one is your superheated steam. Okay, so how these qualities are classified? Okay, so these classification, how these qualities are classified is detailedly explained in the previous lectures. If you have any doubt, you can go through the previous lecture. Okay, so just I am recalling that. So if we say the given specific enthalpy is lesser than the specific enthalpy of saturated vapor, then it is called as a wet steam. Okay, when a given specific enthalpy which is equal to saturated specific enthalpy of vapor, then they are called as dry steam. Okay, so here x value which is equal to 1 here. Okay, then if we say it is a superheated steam, then the specific enthalpy of the saturated vapor is lesser than your given enthalpy. Okay, so this will be applicable for your specific volume also. Okay, for instance, so the given specific volume is lesser than the saturated specific volume of the vapor, then it is called as a wet steam. When the given specific volume and the saturated specific volume of the gas which is equal, they are called as dry steam. When the saturated specific volume of the vapor which is lesser than your given specific volume, then it is called as your superheated steam. Okay, since the same condition will be applied for your specific entropy also. When coming on your temperature, we should say it is a saturation temperature. Okay, so we all know what is saturation temperature. So at this point the phase changes will occur. So in this saturation point, the given temperature is lesser than your saturation point, the steam will be of a wet steam. Then your given temperature which is equal to the saturation temperature, then it is a dry steam. Then the saturation temperature is lesser than your given temperature, then it is known as the state of the steam is your superheated steam. Then, so based on the qualities wet steam, dry steam and superheated steam, we should know some of the basic properties and how to use the formulas for your basic properties. Okay, so first one is your specific enthalpy, the unit is kilojoule per kilogram. If we say the steam is wet, the condition is the given specific enthalpy is lesser than that of your saturated specific enthalpy, then H is equal to HF plus X into HFG. Okay, where H is your specific enthalpy at liquid stage. Okay, so this is your combination of both, so liquid and gaseous vapor. Okay, so X is nothing but your dryness fraction. Okay, what is meant by dryness fraction? That is the amount of, that is the mass of vapor present in the total amount of the steam. Okay, so that is mg by mf plus mg. Okay, X equal to mg by mf plus mg. Then if we say dry steam, I already told that X equal to 1. You substitute your X equal to 1, then it becomes HFG. Okay, so HFG can be written as Hg minus HF. So plus HF and minus HF will get cancelled. Again the term will be H is equal to Hg here. For superheated, so H is equal to Hg plus Cp, that is the constant pressure of the superheated temperature values. Then your T superheated minus your T saturation temperature. The difference between your superheated and saturation temperature. For specific volume, again for a wet condition, V is equal to Vf plus X into Vfg, and for dry steam it is V is equal to Vg, and for superheated steam V is equal to Vg into T sup by T saturation. And also for your specific entropy, S is equal to Sf plus X into Sfg, where S equal to Sg. Here for superheated, S is equal to Sg plus Cps of log into the ratio of T sup by superheated temperature divided by your saturation temperature. And also work done. So we also know that the flow work is equal to P into V. So that is work done is equal to P into V for all the three cases. But this volume, the specific volume will be varied according to these three different conditions. And also know the specific volume is instead of the reciprocal of your density, or otherwise density can be written as 1 by your specific volume in all the three cases of your quality of the steam. Then the specific internal can be determined by H is equal to U plus PV relation. So with this we can write U, specific internal energy U is equal to H minus PV. So this H, the specific enthalpy and the specific volume will be depend on these formulas. What are all the state of the conditions? So corresponding state of the conditions, the signal energy will vary, but the formula for the internal energy for all the three cases are same. Okay. Problem 20. A mass of 0.9 kg of steam initially at a pressure of 1.5 megapascal and at a temperature of 250 degrees Celsius. Here the mass of the steam is given, that is M is equal to 0.9 kg. The initial pressure P1 is equal to 15 bar and the temperature T1 is equal to 250 degrees Celsius, and it is expanded to a pressure of about P2 is equal to 1.5 bar. Assume the process to be isentropic. If we say it is isentropic, the entropies are equal. Okay, so entropies are equal in this case. So this some of the components in your thermodynamic applications, the most of the applications are isentropic. For example, a turbine is an isentropic process. Okay. Find out the condition of the steam and work transfer in this case. Okay, so we need to find out the condition of the steam. We have to check the condition of the steam at both the state 1 and state 2, and also we need to find out the work transfer for your isentropic process. So for that, at saturated water and the steam pressure table, at 15 bar pressure, we have to check the saturation temperature as 198.3 degrees Celsius. The given temperature is 250 degrees Celsius. So the initial condition of the steam is superheated because the saturation temperature is lesser than your given temperature. So the condition of the steam at the state 1 is superheated. Again, you go for your superheated steam table to take the entities of specific volume, specific enthalpy and specific entropy. So specific volume of the superheated steam table at pressure P1 is equal to 15 bar and the temperature T1 is equal to 250 degrees Celsius. You can take the specific volume P1 as 0.152 meter cube per kg. So in the similar way, you can take the specific enthalpy of your superheated steam table at pressure P1 is equal to 15 bar and temperature T1 is equal to 250 degrees Celsius. You can take the specific enthalpy H1 is equal to 2923.5 kilojoule per kilogram. And also we can take it out the specific entropy from your superheated steam table at pressure P1 is equal to 15 bar and the temperature T1 is equal to 250 degrees Celsius. You can take the S1 as 6.710 kilojoule per kilogram Kelvin. Since we know that this problem is of about isentropic process, so we can say S1 is equal to S2 is 6.710 kilojoule per kilogram Kelvin. As we all know, at the second state the pressure is given, so we need to find out the condition of the steam. So for that you have to check out the values from your entropy. Okay, so the constant pressure table P2 is equal to 15 bar, you have to take this Sg value because the comparing value will be Sg, because since it is an isentropic process, so we know that S1 is equal to S2, right? So Sg2 will be 7.223 kilojoule per kilogram Kelvin. As we all know from the previous slide, S1 is equal to S2 is equal to 6.710 kilojoule per kilogram Kelvin. So which is lesser than your saturated vapor, right? So that is S2 is less than your Sg2. The condition of the steam at the state 2 is wet. So if it is wet, we need to find out the dryness fraction X, right? So for that we need the data, that is SF2 and SFG2, and also I am taking all the values VF2, VG2, HF, HFG and HG, SF and SFG2. Okay, to find out work done also we need all the values, so I have taken all the values here from the steam table. So you write S2 is equal to SF2 plus X2 into SFG2. Since the second condition the steam is wet, so you find out X2 and also you find out H2. H2 is equal to HF2 plus X2 into HFG2. Supply all the values and X2 value here, that is 0.911. So substitute those values to get H2 is equal to 2495.25 kilojoule per kilogram. And also the specific volume V2 is VF2 plus X2 into VFG2, that is V2 is equal to VF2 plus X2 into VG2 minus VF2. So substitute all those values to get entities and substitute the simple relation to get the specific volume V2, which is equal to 1.0559 meter cube per kilogram. So we need to find work done in this case. So since Q is equal to work done plus delta U from the first law of thermodynamics, so as we all know, since it is an isentropic process, so there is no area under the temperature entropy curve, so heat transfer is 0 in this case for isentropic process. Okay, so Q is equal to W plus del U we can write. So W is equal to minus delta U, so W is equal to minus of U2 minus U1, so that is W is equal to U1 minus U2. So we know that H is equal to U plus PV, so from that relation we can derive U is equal to H minus PV. So I am substituting this. Work done is equal to H1 minus P1 V1 minus H2 minus P2 V2. So substitute all those entities to your work done as 358.64 kilojoule per kilogram. Okay, so this is your specific work done. Okay, that is work done per unit mass, not specific work done, it is work done per unit mass, but here the mass is given, right? So your work done will be work done per unit mass multiplied by your mass. You will get the total work done or net work done will be 322.776 kilojoule. So as a result, the condition of the steam at state 2 is x2 is equal to 0.911. The condition of the steam is wet in this case. So work transfer W is equal to 322.76 kilojoule. So as we all know, we have solved this problem by using steam table method. Now we are going to solve this problem by using Mollier chart method. See, these are all the conditions given, that is P1 is equal to 15 bar and P2 is equal to 1.5 bar, temperature T1 is equal to 250 degrees Celsius, and also it is an isentropic process. So with this 4, we can find out all the values what we have solved in the steam table method. Okay, so this is your Mollier chart. In x-axis you are having specific entropy and y-axis you are having specific enthalpy, and this is your saturated line. So below the saturated line where the point will be marked as wet condition, the above the saturation line the point as superheated steam, right? So first one, here pressure is equal to 15 bar. You check it out for pressure is equal to 15 bar line. Okay, so this is your pressure is equal to 15 bar line, and the temperature is 250 degrees Celsius. So this is your temperature curve. So here the temperature is 250 degrees Celsius. So mark this point as 1. Okay, so this point will be 1. So at this point you can take, you draw a horizontal line to take the enthalpy value. Okay, so enthalpy value H1 is equal to 2920 kilojoule per kilogram Kelvin, and you can draw one vertical line. So from this vertical line you can take the entropy S1 is equal to 6.710 kilojoule per kilogram Kelvin. Okay, then here you can take the specific volume also. Okay, so this is your dotted line. So here the dotted line will be 0.1 and 0.2. okay, so between this it is in middle, so we can write 0.15 in this case. You can observe this line, so this dotted line, these two dotted lines, so you can observe this point. So this is will be of 0.1 and this is will be of 0.2. so this point is in between of 0.1 and 0.2 line, so it can be written as 0.152, right? Then as we all know, since it is an S1 is equal to S2 process, so at the second point how we can mark, already we have drawn a vertical line to take it out S1. So since it is an S1 is equal to S2, that is pressure is P2 is equal to 1.5 bar. So you check it out for 1.5 bar pressure. So at 1.5 bar pressure you draw one line and mark the second point. So this is your second state of the condition, that is your 2. Okay, so at this point you take the enthalpy value H2 is equal to 2495 kilojoule per kilogram. Okay, and also you can take V2. So since this line is of about V2 is 1 and this is of about 2, so this is of 1.055, it is more or less equal to 1, so we can write 1.05 meter cube per kilogram. And also x2, so at this condition the steam is, initial condition the steam is superheated because it is above the saturated line, and the second point it is below the saturated line, the condition of the steam is wet. We have to take the dryness fraction. So here you observe that is 0.95 and 0.9, so we can say it is x2 is equal to 0.91. Okay, so with this we have taken all the values what we have needed to find out. So I have written all the values that I have taken from the Mollier chart, and again following the same procedure what I have did in the steam table method. So since it is an isentropic process, so heat transfer is 0 in this case, there is no area under the work done in a TS diagram, so Q is equal to 0. So work done is equal to minus delta U. So work done is equal to minus U2 minus U1. So that can be expanded as H1 minus P1 V1 minus H2 minus P2 V2. Here on this case we need to keep it, remember you have to substitute the pressure in terms of kilopascal, right? And work done will be 355.38 kilojoule per kilogram. This is work done per unit mass, but the mass is given in the problem, so you take work done is equal to 355.38 kilojoule per kilogram into mass as 0.9, multiply with mass as 0.9, then work done will be 319.84 kilojoule. So as a result, the condition of the steam at the initial stage is superheated and the final stage is wet, and work transfer is 319.84 kilo.